Hello guys, welcome to homework 25. I'll be going through the problems now with you guys. So the very first problem we have here, let me enlarge this so you guys can see better. It says, which one of the following statements concerning spherical mirrors is correct? It says only a concave mirror can produce an enlarged image provided the object distance is greater than the radius of curvature. No. So both concave and convex mirrors can produce an enlarged image now. So if you want to understand this part, I'll advise you guys to watch the video for recitation before you watch this video of the homework, because in the recitation, I took my time to explain the different images formed on a convex mirror and a concave mirror, and depending on the position of the object. So if the object is beyond the center of curvature, you're going to have a real inverted image between F and C. If the object is at C, you have the image at C, same size as object, inverted. And if the object is between F and C, you have image beyond C, magnified. So that will give you, if you understand those steps as you bring the image closer to the mirror, it will make you understand how to answer this problem. So the correct answer is C. It can produce an enlarged image provided the object distance is less than the radius of the curvature. Okay, less than. So between F and C, you're going to have an enlarged image. At F, you're going to have an enlarged image at infinity. And then between F and the mirror, you have an enlarged image, which is virtual behind the mirror. So C is the correct answer. A convex mirror never produces an enlarged image. Irrespective of where the object is placed, the convex mirror always produces a small, diminished, upright image that is virtual behind the mirror. Okay, so like I said, to understand the different images formed and how they are constructed, watch the video for the recitation first, the recitation quiz before this. It will make you understand this better. All right. Focus on concept question 13 says, suppose you hold up a small convex mirror in front of your face. Which answer describes the image of your face? So the image of your face is going to be virtual and upright for sure. So since it's a convex mirror, it's going to be diminished too. It's going to be smaller than the object. Okay, so A is the correct answer. Real, never. Enlarge, never. Real, never. Inverted, excuse me, never. If convex mirror always provides an upright image that is diminished. Okay. An object is placed, that's the focus on concept question 14. An object is placed at a known distance in front of a mirror whose focal length is also known. You apply the mirror equation and find that the image distance is a negative number. This result tells you that when you have a negative number for image distance, it just tells you the image is virtual. Okay. Or if you get a negative number for focal length, it tells you the mirror is convex. A convex mirror has a negative focal length. A concave mirror has a positive focal length. So a negative distance means the image is virtual. That's the correct answer. It has nothing to do with the magnification. It just tells you. And it could also tell you if the image is inverted. That has to do with the magnification. So if your magnification is negative, that is what tells you the image is inverted or upright. But just the distance is negative. It tells you the image is virtual. All right. So next, chapter 25, problem 19 says the image produced by a concave mirror is located 38 centimeters in front of the mirror. So that's your distance of object. Okay. Distance of image, the image produced. So that's your DI. And then the focal length is given, and it's a concave mirror. So your focal length is going to be positive, and they're asked to find the object distance, DO. So 1 over DO plus 1 over DI is 1 over F. There's the mirror equation. So if you take 1 over DO equals 1 over F minus 1 over DI, you just put your focal length to be 25 and your DI to be 38. So since the image is in front of the mirror, it's a real image. That's image formed in front of the mirror. So it's going to be positive. If it was virtual behind the mirror, then we're going to put a minus sign there for the 38. So it's 1 over F minus 1 over DI, both of them positive under, and then you get your D naught by taking the inverse of this subtraction. I need to give you that answer. So we'll go to chapter 25, problem 20. So the image behind the convex mirror, radius of curvature, this is that. So you're going to see your DI is negative, your focal length is negative because it's behind the mirror. The image is virtual. And at the same time, your mirror is a convex mirror. So the focal length is negative. So they're asked for you to find object distance. So just using this two, we can find 1 over D naught. So both are negatives now for F and DI. From there, we'll get D naught to be positive. The object was in front of the mirror. Then the next is to find the magnification. So magnification is negative image distance over object distance, or image height over object height. So if you're using image height over object height, you don't use negative. The negative only comes in the distance part. So when you put the negative here, you're going to get a positive number. So it tells you that the object is upright. Remember? So it's a positive magnification, even if the image distance is negative. So the image distance is negative tells you it's a virtual image, but it's also upright. A convex mirror always produces an upright image, but it's smaller than the object. So because the magnification is less than 1, you can tell it's smaller. This is just an addendum to explain. It's not part of the problem. C and D. It's just explaining. So since magnification is positive, the image is upright. And since magnification is less than 1, the image is smaller than the object, as expected for a convex mirror. Okay. Chapter 25, problem 21. So a concave mirror radius of curvature given is used to project a transparent. So this radius of curvature is different from the focal length. Focal length is half of this. So you're going to see your focal length is half of radius of curvature, which is 30.8 right here. When you divide this by 2, okay? Onto a wall, the slide located at the distance that from the mirror. So that's going to be your, this one here is your object distance, and a small flashlight shines light through the slide onto the mirror. How far from the wall should the mirror be located? So they want you to see the image distance. So we want to find the image distance. 1 over focal length minus 1 over object distance, you get that. And then the height of the object on the slide is given, and what is the height of the image? So we can use negative image distance over object distance to get magnification. And then magnification is the same as image height over object height. So image height is magnification times object height. And magnification is negative image distance over object distance times object height. That gives us image height right here. Okay. So we're combining the two formulas for magnification, image height over object height or negative image distance over object distance. So when we do that, we get our image height to be this. So the image height is negative. So it tells you it's upside down if the height is negative. If the distance is negative, it's virtual. If the distance is positive, it's real. If the height is negative, it's upside down. If the height is positive, it is upright. Okay. Next, chapter 25, problem 23. A mirror produces an image that is located 22 centimeters behind the mirror. So it's a virtual image. So we can't tell yet what kind of mirror it is because even a concave mirror can have a virtual image if you place the object between the focal point and the mirror, the pole of the mirror. And a convex mirror always produces a virtual image. So now we are confused. So when the object is located 5.1 cm in front of the mirror, what is the focal length? So we calculated the focal length of the mirror is 6.64. So focal length is 1 over D object plus 1 over D image. So when you get 6.64, 6.64 is more than the object distance. So it means the object is between F and the pole. So that is a concave mirror. That is a concave mirror. Okay, that is a concave mirror. Okay, since the focal length is positive, so first of all, the focal length is positive, and then secondly, you could tell that is between the focal point and so if we had a negative focal length, it doesn't matter if it's 6.64 centimeters, it will just automatically be a convex. So that is one red flag to check. Once you have a positive focal length, it's a concave mirror automatically. Okay, next problem. Chapter 25, problem 25. The outside mirror on the passenger side of a car is convex and has a focal length of -6 meters. Relative to this mirror, a truck traveling in the rear has an object distance of that. Find the image distance. So just 1 over DI is 1 over F minus 1 over D0, you get that. So the image is negative because it's a convex mirror, as expected. Then, because it's virtual all the time, then we want to find the magnification. So negative image distance over object distance, negative distance, so it becomes positive because the object is upright. The object has to be upright. Okay. Convex mirror has a focal length of -25 cm. Find the magnification produced by the mirror when the object distance is this and that. So first of all, When we have the focal length given, we can find the image distance. So image distance is 1 over focal length minus 1 over d object, or d image is f d object over d object minus f when you simplify this. Then magnification is negative d image over d object. So that's negative this guy, which is d image, f d object over d object minus f all over d object. So we are given f and d object. That's all we're given. So we have the magnification in terms of that. So for the smaller object distance, when f is negative 25 and d object is 12, we put negative 25 and 12 and solve, and we get this. And when f is negative 25 still and d object is 18, we get different magnifications. But in both cases, we can see that the magnification is always less than 1, no matter what, because a convex mirror always produces images less than the object image. Next, when diffuse reflection from a surface occurs, so it means that reflection, the reflected rays are not parallel. So diffuse means irregular reflection. A plane mirror has regular reflection. If I have a rough surface that has contour surface, so the rays, the incident rays will not go parallel with the reflected rays when they go. So the rays are going to mix up because of the rough surface. So that's what we mean by diffuse reflection. The drawing shows the top of an object located at the right of a mirror. A single ray of light is shown leaving the object. After reflection, which location will this ray pass? So you can trace this straight down to this point and go, it will just reflect at the same angle. So it's only going to pass through C. So trace this straight down to the mirror right here and trace it from here down. You see it's going to just pass through C. That's law of reflection, basically. Angle of incidence equals angle of reflection. So the answer is C for this one. And the next one, this drawing shows the top view of an object to the right of a plane mirror. An observer looks into the mirror. At what location does the observer see the image? So the object is here. Is that okay? So the object, this is the mirror. The observer is looking at this object. So whatever distance the object is the same distance is going to be here. So it's just going to be A. So object distance equals image distance and the same position, basically. So a plane mirror has the same object and image distances, the same size. It only has lateral inversion because you have left hand look like right hand in the mirror. So if you look at a plane mirror, wave your right hand, you're going to see it's your left hand that's waving in the mirror. That's lateral inversion. And image is upright for a plane mirror. You see yourself standing upright for a plane flat mirror. Yeah, basically. And you have the same size. Magnification is 1. And the distance of object is the same as the distance from the image. Like I said, watch the videos, the video for the quiz. I explain all the properties of mirrors before I solve the problem. So I don't want to go over that in this homework. Okay, next problem. Rays of light coming from the sun are near and parallel to the principal axis of a concave mirror. After reflecting from the mirror, where will the rays cross each other at a single point? They're going to cross each other at the focal point. So that's the definition of a focal point. It's the point on the principal axis where rays far and parallel in incident on the mirror appear to converge after they reflect. That's how they would define the focal point. Is that okay? So when rays come to a mirror and reflect parallel far rays from infinity approximately, they converge at the focal point. So that's why B is the correct answer. And then light rays are near and parallel to the principal axis of a concave mirror and converge to 0.18 centimeters. So this is the focal point, basically. So that's the point where parallel rays far away and parallel and near to the principal axis appear to converge. So they asked to find the radius of curvature. Radius of curvature is twice focal point, or twice focal length, which is 2 times 18, and that's just 36 centimeters. That's the correct answer. So you just multiply the focal point by 2, you get your radius of curvature. This is the end of the homework. I'll see you guys next week. Have a good one, guys, for now. Thank you.